Last week we have studied peck learning, probably approximately correct learning. So this is peck learning. Essentially, when we have finite hypothesis class, so a hypothesis class has finite hypothesis element. There exists some sampling low bound, which can guarantee once you collect more than the lower bound, your ERM rule, empirical error minimization rule, empirical risk minimization rule can guarantee epsilon accurate with probability 1 minus delta. So we have discussed the sample complexity, and we show some theorem with concentration inequality. Okay. So this time we will discuss bias and complexity trade-off, or called bias and variance trade-off. Essentially, when we consider very complicated hypothesis class, so a lot of hypotheses there, with a high chance the ground truth, the true distribution that really generate the data set, can also belong to the hypothesis set if the hypothesis set include a lot of different functions. But as we discussed last time, as the number of hypotheses increase, the sampling complexity, the required number of samples to guarantee peck learning also increase. But if you use too simple hypothesis class, on the other hand, with high chance the true hypothesis function does not belong to the hypothesis set you are considering. So there is trade-off. If you use too complicated hypothesis set, then you need a lot of samples. You need a huge size of training set. On the other hand, if you use too simple hypothesis set, then with high chance the true hypothesis is not a member of your hypothesis class. So there exists some bias error. So this is a bias and variance trade-off, or bias and complexity trade-off, and this is the key part of machine learning. In most of machine learning researches, we always try to figure out how to control the bias and variance trade-off. Okay, let's start. So the first part of this chapter is universal algorithm, the definition of universal algorithm. So what is universal algorithm? So can we design a good algorithm having zero error or almost zero error without any knowledge on the data generation model D or hypothesis H? So essentially, in the previous week, we considered two types of different data generation process. One is we just randomly generate input X or input element X, which is randomly generated according to some given distribution D, and the corresponding labels are assigned by function H through hypothesis H. And we usually assume H belongs to our hypothesis class, but in reality, we cannot guarantee this. We cannot guarantee the true hypothesis belong to our hypothesis class we are considering now. The second case was this. There exists a distribution D which defines both input and output. So D is a probability distribution over both an input and output space. Previously, we assumed that the true hypothesis class belong to the hypothesis class we are considering. But consider the case that there are two hypothesis sets, H1 and H2. In H1, the cardinality of H1 is much bigger than cardinality of H2. So in other words, the complexity of H1 is higher than the complexity of H2. we have more flexibility with hypothesis class H1 compared to the hypothesis class H2. For instance, H2 is a linear regression model. H1 is very complicated neural networks. Then parameters defined by the neural network has more flexibility compared to the linear model. So which hypothesis set is better if H belongs to both H1 and H2? This is very important question. If the true hypothesis is member of not only H1 but also H2, then since we know that H1, the cardinality of H1 is much bigger than H2, and from the previous week, we studied peng learning and sample complexity for the peng learning guarantee, where the cardinality of hypothesis set define the row bound of sample complexity, and usually as the cardinality of our hypothesis class increases, then the sample complexity also increases as well. So when we have this condition and when the ground truth H that generate a corresponding label belong to both H1 and H2, definitely H2 is better hypothesis class. And the second question is, which hypothesis set is better if the true hypothesis H belongs to H1, but H does not belong to the second hypothesis class? It will happen many times because the first hypothesis class is much complex and much flexible compared to H2. So this is very usual case. Only H1 has the true hypothesis function. In that case, although we require more samples to guarantee epsilon accuracy, since we have the H1 has the true hypothesis H that make a zero test error, we have benefit. When we have this condition, the true hypothesis does not belong to our hypothesis class, then what we can say is just this. We can say compared to the best among our hypothesis class, what is the sample complexity, our outcome by some ERM rule is the test error or test rules less than or equal to our best hypothesis among our hypothesis class plus epsilon. That is what we can say at most when the true hypothesis is not member of our hypothesis class. So when this value is high, when this is high, then the second hypothesis class H2 is just garbage. We cannot make a very precise prediction. While with the first hypothesis class, we can guarantee very nice accuracy with a sufficient number of samples. So this is overfitting versus underfitting. Consider this case there are two classes. I will use circle and cross to denote two class element, and the input located on the 2D space, and each input point assigned to a label, either circle or cross. When we collect these four data points and our hypothesis class, the first hypothesis class is let's say 10 degree polynomial, and H2 is just a linear regression, so degree 1 polynomial. Then with hypothesis 2, our outcome, the result will be some line in between the circle and cross. And if the true hypothesis is also this, then with a very high chance the test error of our ERM rule or our algorithm will be very accurate, right? But with the first hypothesis class, the 100-degree polynomial function, the boundary will be very complicated, like this. I don't know, this also a member of 100-degree polynomial. And this very wiggly boundary can make a higher test error compared to the result, this linear line, right? So with this simple boundary case, with this simple true hypothesis function case, more simpler hypothesis set can be better than more complicated hypothesis class. And this is called overfitting issue. When we use too many parameters compared to the number of data point or compared to the true boundary or true function simplicity or complexity, then our fitting can have a zero training error. So although the training performance is really good, although we always have zero training error hypothesis, so always the ERM rule has zero loss or zero error for your training data, but with respect to the test error, your outcome will be very bad. Okay, this is called overfitting issue, and this was indeed explained by peg running analysis. As the number of elements in your hypothesis grows, then the sample complexity also grows. On the other hand, if your true your trained data point has this shape, the circle has this data point, and cross data point has this data, then maybe the true boundary is this. And the first hypothesis class maybe can make this boundary because we have a very flexible algorithm, so we can expect this boundary from this first hypothesis class. But with this very simple hypothesis class, the linear regression or linear boundary line, and most we can do is just a very rough boundary, very bad boundary, which can generate a rather misclassified data point. Okay, so as you can see, even for the training data point, the second hypothesis class has huge error. So naturally, this already has very huge value. This is called bias error, and this case is called underfitting case.